Alright, so we're going to talk about Kepler's three laws of planetary motion. It's actually any motion where one object is orbiting another, but Kepler originally, 400 years ago, talked about the planets going around the sun. Alright, so Kepler's three laws. Let's start out with the first law, and the first law basically says that planets travel in elliptical orbits. Okay, so this is the first law right here. So in this actually goes against what Aristotle had said and what had been adopted for more than 2,000 years. Well, sorry, more than 1,000 years at the time of Kepler. Is that all the planets traveled in perfect circles, and of course the Greeks believed that the planets traveled around the Earth. In the Middle Ages, of course, or at the end of the Middle Ages, towards the Renaissance, Copernicus proposed a simpler method that of course the sun is the center of the solar system, and all the planets travel around the sun. And this helped explain what's called retrograde motion, the apparent backwards motion of a planet with respect to the stars. So, of course, Copernicus's idea made a lot of sense, but people still didn't accept it. And even during the time of Kepler, which is 100 years or so after Copernicus, people still were not accepting of it. Anyhow, Kepler made these discoveries. So this is the first law: planets travel in elliptical orbits as opposed to circular. This is the first law. And then the second law can be stated several different ways. I'm going to go with the modern way that we talk about. So when a planet is traveling in an elliptical orbit, way out here, it's furthest from the sun, and then it's going to get closer to the sun. Let's say over here. And basically it changes speeds because of gravity. When the planet is closest to the sun, it's going fastest. The instant that it's closer to the sun. So times when it's closer to the sun, it's still moving faster than when it's way over here. And when it's way over here in its orbit, it is traveling the slowest. That's not the way Kepler described this. He actually talked about the planet in its orbit sweeping out equal areas in equal amounts of time. So let's say that the time period here is, I'm just making this up, let's say that this is 1 month. Okay, so the planet goes from this point to this point in 1 month, and then this would be an equal amount of time. Of course, this wouldn't be the Earth, but this would be an equal amount of time. So the planet goes from here to here in its orbit. So this area, it doesn't, this is not very accurate. No, actually, that's not a good drawing at all. This would be a much narrower. Sorry. So it would be like from this point to this point would be 1 month, and so it would be this area. Anyhow, the way Kepler talked about it was the planet sweeps out equal areas in equal times. All right, and then the third law. So that's the second law. You can think of the second law. Okay, so the second law, when a planet is closest, it's traveling fastest. When it's furthest, it's traveling slowest. And this is true for comets, asteroids, anything in orbit around anything, really. And then the third law, as I have down here, says that a planet's distance, or its average distance, that's what we call A. So A would be like this. That's A, this distance here, okay, from the center of the sun to where the planet is. Now, of course, it's getting closer and further, but A is called the average distance, or its technical name is called the semi-major axis. All right, anyhow, and P, of course, is the period. So the time it takes the planet to go all the way around the sun to complete one orbit, of course, that's the period. And the units here for the period, the units are years, because Kepler, basically needed those units to make this equation work. And A is the distance from the sun to the Earth. However, during Kepler's time, 400 years ago, he didn't know what the distance the distance was, or what one Earth-Sun distance was. And so the units that he used are called astronomical units. Capital U. So these are astronomical units, and that is just one Earth-Sun distance. So that's all that is. All right, let's do an example with Kepler's third law, and let's start out by saying you know somebody observes a planet, and let's say that its average distance from the sun is, oh, I don't know, how about 15.6 AU. All right, so it's 15.6 AU, and we want to figure out what its period is. Okay, so what's the period, right? The period equals question mark. See, they're not independent. That's Kepler's third law, that the cube, here, let's go back to this. The cube of the semi-major axis is proportional to the square of the period. All right, and so what we can do is we can take this equation and we solve for p, right? So remember, if you have something squared, solve for p. If you have something squared, of course, you're going to have to take the square root of both sides, the square root of a to the third. All right, and that's going to, now we can put the numbers in, so it's the square root of 15.6. And we're cubing that, we're raising that to the third power, and that equals, let me get my calculator, the answer that I get would be 61.6 roughly, and of course the period is in years. All right, so don't forget, you have to cube the 15.6 and then take the square root of that. All right, let's do another example. All right, so here's our second example. Let's say we observe a planet in orbit. Here's the thing about Kepler's third law, the version that I just showed you, where a cubed is equal to p squared, a is in AU, p is in years. It only works for stars that have exactly the same mass as the sun. Okay, that's really important. This is only for something that has the mass of the sun. Okay, so that's the only time that's true. It has to have, you know, so it can be the sun, of course. That's the way Kepler originally used it. But you know, we find other stars that have the same mass as the sun. So if they do, we can use this equation. And so what we're going to do now, in this second example, let's say that you observe. This could be some alien planet, some planet around another star that happens to have the same mass as our sun, and you observe that planet takes 200 years to go around its star. And so what would be the distance, the average distance, or another way of saying that is the semi-major axis. We'll find A. And so you have, of course, Kepler's third law. There it is. And we have to solve for A. And so to solve for A, since A is cubed, we have to take the cube root of p squared. And just to remind everybody what that means, that is p is raised to the second power, but then we raise this. Remember what a cube root is, just like what a square root, you know, a square root is raising something to the 1/2 power. So a cube root here is raising something to the 1/3 power. All right, so now let's set it up. There we go. So A is equal to 200 squared, 200 years, of course, it's got to be in years, squared. And then, of course, we know that our answer is going to be in astronomical units. And then we raise that to the 1/3, or you know, the cube root. It's the same thing. It means the exact same thing. All right, let me get my calculator. Let's see what the answer is. Okay, so you know, some people's calculator have already have a cube root. If you have a Texas Instruments that, like I have here in front of me, you can hit the mode button, and that will oh, sorry, not the mode button, the math button. Here, let me get out of this. The math button, and if you go down, there is a cube root. Okay, so you can actually do that. Anyhow, so we square the 200, and you get 40,000. But then you have to take the cube root of that, and the answer that I get is 34. I'm going to round here, 0.2, and that of course would be in astronomical AU, astronomical units. Okay, so that's there's our answer, 34.2 AU. All right, so there's two examples, and that's just the way this works. You do it the same way each time. All right.